numbers in chat box. In last class, we were looking at the aspect of this perceptron, how it is working. So this was my initial weight. I was standing here and my answer is negative because my input was belonging to class 1. It is pointing towards this side of the line. So this side of the line becomes positive side or positive value of that discriminant function. Okay, so W transpose Y1 is greater than 0 for all this shaded region, and W transpose Y1 is less than 0 for white region, and on this line it is 0. So since my input belongs to class 1, if I stand here anywhere in this space, then my answer is negative. So I want to get positive answer, so I should move from this point to this side, above this line. Okay, so I can follow any path. I can move from, say, this point to this point or any point like this, but I should go with the steepest path, with the shortest path. So this is the shortest path. So shortest path is nothing but gradient of W transpose Y function. Okay. So gradient of this will give you actually Y1, that is nothing but your input vector. So we add a small portion of that vector to the weight vector. It means it will move from this position to next position when I add delta W. What is delta W? Delta W is this vector small component. Okay, so this vector, a small component, how I will get? I will multiply this vector Y1 by some small number in the range, say 0 plus to 1. So if I take that multiplication, I will get a small vector like this, and I will move from this W1 to, let us say, this position. So in next iteration I will go here, next iteration I will go here, and finally I will cross this barrier or this line. So note that Y1 belongs to class 1, and then we add the direction of delta W as Y1. Okay, so when delta W is, when this delta W is added to W old, so W new is equal to W old plus delta W. So this will occur when input is class 1 and current output is equal to -1. So desired response is +1 and actual output is -1. If this is the situation, then you are going to add to the current weight. Opposite will be the case like this, that your input belongs to class 2, you want negative output, and you are obtaining positive output. So desired response is -1, output is positive +1. If this is the case, then you need to subtract from current position. So this will be W1. So you will be subtracting so that you will move to this side. So this will be W new This is W old, and this component is C into Y1. So this is getting subtracted. Okay, so when you take gradient of W transpose Y1 in this case, you will get this direction. But since you want to move in opposite direction because you want negative output, so you will reverse this vector by multiplying by -1. Okay, so this negative thing will be added to existing W. That means we are actually subtracting this gradient of W transpose Y1. So you will move in this direction. So you can note down this W new is equal to W old minus CY1. So when you will do this, when you want desired response is negative and your output is positive. You can see here, this side is W transpose Y greater than 0. So this is a positive zone and you want your weight to be in negative zone. Okay, you are just adjusting weight. What is in your hand? In your hand, to get correct answer, you have to adjust weight. Okay, so you have now two options for correction. The change in weight can be positive or it can be negative. It can be added or it can be subtracted. Based on the situation, you will do this. So I can write in general as W new is equal to W old plus or minus C into Y, that is input. Now we took this example earlier also. Say I am standing here, my input is Y1 which is belonging to class 1. So if I stand here in weight space, Y1 is this direction. So this becomes positive and this becomes negative. So when I take the product W transpose Y1, it will give me negative answer. So I should move this W here. So this will be my new position. So if I put now my weights here, this will produce W transpose Y1 greater than 0. So output is positive. That is what I want. Since it belongs to class 1, and I assume that for class 1 my response will be positive and for class 2 my response will be negative. Now let us take a 3 sample case. It's a simple problem and we have 3 patterns which are presented to us. Now this is weight space W1, W2. Okay. Now see what is given to us. So this is pattern number 1. The direction is this. It belongs to class 1. That means for this particular pattern number 1, I want positive response. Now initial weight, so this is W1, which is initial weight. So I have randomly assumed that my weight will stand here. I don't know what is solution. So whenever I start my neural network, I start with random assumptions of weight. What it means, throughout this space, you are standing or choosing to stand randomly at any position. So you can start here, you can start here. Since this is a 2D case, you can visualize. If it is multidimensional case, you cannot actually visualize such kind of scene. Now for the simplicity, we are taking a 2D case and assuming that this is my initial weight. So initial weight is here, which belongs says, and I have been presented a pattern Y1 which belongs to class 1. So if I take W1 transpose Y1, what it will be? As per this diagram, Y1 is in this direction So this side of the line is positive and back side of the line, this side is negative. And you can see your weight is standing here. That means your answer will be negative. So what to do? You add now a component of y1 in this direction and change your weights, say from w1 to w2. So what will happen? You are now moving from this position to this position. Okay, so you have crossed this line where w transpose y1 is equal to 0. Now you have crossed this line, so you will reach here. Now this is the positive zone, and you want that because you want for class 1 output should be positive. Now you are in the positive zone, so because of this correction, your pattern 1 is now correctly classified. Okay, so this is done. Now I am here. Now I have been presented the second pattern, which is y2 of this direction. Okay, and it also belongs to class 1. Okay, now if it is belonging to class 1, I want my weight to be in the positive zone of this particular line. Which line? This line. How I obtain this line? So this was given to me, y2 is given to me. Suppose I draw here, y2 is given to me. Draw a perpendicular line. So that becomes my decision boundary. So why it is like that, we have seen in previous classes. You can read the books or you can just go through those videos again. You will see that whenever I present a pattern like this, a perpendicular line to that will give you W transpose y2 equal to 0 line. So this is I am talking about weight space, augmented weight space. Okay, so if I have another pattern, say maybe something like this, y3, then perpendicular to that, if I draw a line passing through origin, then this line is W transpose y3 equal to 0. So this is the decision boundary. Remember, this side, the direction of pattern is always positive and the opposite side is negative. So like that, if I draw this y2 here, actually I can draw here. I should draw actually here because those are the vectors to be drawn from the center of the axis. But moving vectors throughout the space doesn't make any problem. So I am moving this vector y2 from this position to this position. So that will not hamper my calculations, or it will not change the solution. So I will draw here this vector y2 and then I draw a perpendicular line, which is the decision boundary W transpose y2 equal to 0. Now you can see here I am standing in the back side of this line. So this is the negative zone because my vector is in this direction. So this is positive zone for y2 and this becomes negative zone for y2. So be careful what I am saying. I am saying that this is the positive zone for pattern y2 and this is negative zone for pattern y2. What you want, since it is class 1 sample, you want that weight should be in the positive zone. But where is weight? Weight is here, which is in the negative zone of this decision boundary. So I should move this in this direction, so that it will cross this boundary and it will go here. Okay, so this will again add some value along this y2 direction, and it will move this w2 to w3. Now if you put your weight at w3 position, what will happen is your y2 sample is now correctly classified. So this position y2 is now classified correctly. What will happen to your y1 sample? What y1 was saying, that you go this side of this particular line, and you can see here your weight is in this direction. So y1 is also correctly classified because your weights are in the positive zone of y1 as well as positive zone of y2. So both y1 and y2, they are classified correctly. Okay, now what about third pattern? So when you present third pattern, that is y3. So where is this y3? This is pattern 3, which now belongs to class 2, and this has this direction. Okay. You are standing here, and you are now being presented with third pattern, which is y3. Y3, what it is saying, this is the direction where your W transpose y3 is greater than 0, and this direction W transpose y3 is less than 0. Now what you want? Since this is a pattern which belongs to class 2, you want negative output. Okay, you want negative output, but since you are standing here, which is the positive side of the y3 pattern, okay, your answer is wrong. So what you have to do, you have to move this weight again with the shortest path and go above this line. So if you travel with the shortest path, that is gradient path, in this direction, how you can travel like this? You want to travel in the opposite direction of y3, remember. Okay, so you will travel in the negative direction of y3. So y3 you will multiply by a small component, small number, so that it will give you a small component. So cy3, and you will subtract from current weight. So current weight is w2 minus cy3, or w3 rather. So w3 minus cy3, so you will get w4. So w4 is standing here. Now what will happen to this pattern now, y3? Since y3 positive direction is this side of the line, this side of this line, but you are opposite, you are standing in the opposite side, say here, then you will get a negative response which you want. Now are the patterns y1, y2 still classified correctly? Can you check that? So we can check that. So if I suppose clean this thing, okay, so let us see if everybody is satisfied. Now if I take y1, it is saying go this side, so go this side. Okay, so if I take this weight, it is obviously in the right position. So if I take now y2, this pattern, it is saying that you go this side of the line. So obviously y4 weight is in the correct position. So it is satisfying y1 as well as y2. What about y3? So y3 is saying you go in this direction. So if you find out the intersection of all these zones, three zones defined by three patterns, this shaded area is the solution zone. So if you stand anywhere in this zone, anywhere, so if you stand anywhere in this zone, all patterns are classified correctly. Okay, so once you reach here, you did not change your weights. So we say that your perceptron or neuron is trained for given samples. So I hope you have understood now what this perceptron learning rule is doing. It is checking given input pattern whether it is producing correct answer or not. If it is producing wrong answer, it is changing the weight position from one zone to other zone. Now remember, this may not happen in one iteration. So you are presenting one by one all the patterns and you see that your answer is correct. So that is not going to happen. So since this is a theoretical graphical representation, we can visualize and we can see what is happening. Now, when it's practical, you really don't know what should be value of C, what should be step size. So C is what? C, the constant, controls the step size. So if C is very small, your initial weight is suppose here, then you may reach here. Okay, next iteration you will go here and so on. Okay, if C is very big, you can jump from this position to this position. So this should not happen. So you should have a moderate value of C so that this step size is controlled properly. So generally we keep the W say C of the order say 0.1 or maybe C 0.05 like this. Okay, so don't put big value of C, otherwise you may jump, say for example, let us say you are now at this position and you have been presented pattern 3 and you keep your C value very large. What will happen? You will jump from this point W3 to this point W4. So you will cross whole this solution area and you will be thrown here. What will happen? If you are standing here, then all the all these input patterns are not classified correctly. Can you see which pattern is not classified correctly if I stand here? Suppose my final weight is suppose here. Are all patterns classified correctly? Can you check? How to check? Again, go to this basic thing. What y1 is saying? Y1 is saying go this side, and see what happens. You are not on this side of the line, so y1 itself is not classified. Okay, so maybe remaining things are classified, but y1 is not satisfied. That means your training is not over. You have to move from this direction, this position to this solution zone. So if you take any point in the solution zone, all are satisfied. Okay, that is what we can see from the diagram. Now try to solve this problem where we have I think 4-5 patterns, and question is find area of convergence, that is the area of solution. So you can start from any pattern actually, but we will follow the sequence of the patterns that is given to us. Suppose I am assuming a sequence 1 3 2 4 5, suppose like this. If I go, then this pattern y1 is given to us, which is here, which belongs to class 1. That means my weight must be above this line. Okay, my weight must be above this line. Now if I take, suppose pattern 3 y3, y3 belongs to class 2. That means this is the positive side of this W transpose y3, and this is the negative. Since my y3 is belonging to class 2, what this pattern is saying, go above me, say go like this. So if you want to satisfy both y1 and y3, your zone is now squeezed only this much. Okay, you cannot be somewhere here or you cannot be somewhere here. You will not satisfy both. So you have to satisfy both. That means you must be within this cone. Okay, so you must be within this zone. Now y1 is satisfied, y3 is satisfied. Let us take pattern 2. Pattern 2, that is y2, belongs to again class 2. What is direction? This is direction of y2. Since it is class 2 pattern, this direction is of positive side and this direction is of negative side. Since I want negative answer for class 2, my zone is this side. Now see, I want to satisfy y1, y2, y3. If I take this complete zone, then I was satisfying y1 and y3. Now if I want to satisfy y1, y2, y3, then zone is further squeezed to this much. Okay. Now let us present the fourth pattern. Fourth pattern is this one, and it is oriented like this. It belongs to class 1. That means you want that weight W transpose Y4 must be greater than 0. That means you should keep your weights above this line. This is the positive zone of the line, so I should move my weights in this direction. So what has happened? This zone is further squeezed from this point to this point. Okay, so your weight must be in this cone so that y1, y2, y3, y4, all of them are satisfied. Now one more is left. So one more is y5. So y5 belongs to class 2 and direction of y5 is this one. That means since it is positive direction, I want negative direction, so I must be in search of this negative direction like this. So our solution is further squeezed and and this is the common area. So this is the common area that we were looking for. So if your weights are within this zone, within say this zone, all patterns are classified correctly. Okay, so what happens is when you randomly assume weights, suppose my weights are here, then because you are presenting the patterns one by one, this weight will slowly move from all these different areas and it will land to this. Okay, it may go in this direction, it may go like this, depending on the sequence of pattern. So finally it will land to this area, and once it lands to this shaded region, no further training is required. Even if you iterate, your algorithm will not move these weights. So this is the area where if you keep your weights, we say that your neuron is trained. No further training is required. And this process is called as training of a neuron or a neural network or learning of a neuron. So both are same. So you can see here a clean diagram where this is the shaded region where if you keep your weights, all patterns are satisfied. Okay, I hope you got the basic idea of perceptron learning rule. So this happens in perceptron learning rule. What was that rule? Change in weight is equal to C into D minus O into X. Okay, so this was the pattern, input pattern D minus O. So when you say W new is equal to W old plus this thing, so D minus O plays the important role of adding or subtracting this vector X from the current weight position. So when you say desired response is +1 and output is -1, so what will happen? D minus O is 1 minus minus of 1. So this will be +2 and it will get multiplied with this C. So C into +2, a small portion of vector X is added to W. Now when I say desired response is -1, output is +1, so again a wrong thing. So C into D minus O, what will happen? So C into -1 minus of 1 into X. So this small portion, since I am putting C equal to 0.1, then this will be minus 0.2 into X. So this small vector is subtracted from current position of weight. So this is happening automatically, you need not worry. Once you implement this D minus O, this is taken care of. So what is required in your program, you start with some for loop, say pattern xi, where I is from 1 to suppose n, and then you execute a loop for training, say W is equal to W old plus delta W, where delta W is C into D minus O, that is DI, I should write OI into pattern number, say xi. So if you try to implement this, it will take care of everything. So as a revision, you can see, in fact, Perceptron is doing the same thing. Change in weight is c into d minus o into x. So you will add when x belongs to class 1 and your answer is negative. If x belongs to class 1 and your answer is positive, what you will do? You will do nothing, because this is already trained. So desired response is +1 and your output is also +1. So what will happen? Automatically this will be 0. Okay, so there won't be any change in weight. Similarly, when you have desired response -1 and you obtain -1, so this will be -1 minus of -1. So this will be -1 plus 1. So again it will be 0. So for correct answer, no training. When your neuron is producing correct answer, you will not train your neuron. Or it is already giving you correct answer, why to train it? So that will be also happening automatically. So what this d minus o simple thing is doing, it is controlling everything. So this d minus o is very important. So it is checking whether you want positive answer and you obtain negative answer, what to do. When you want negative answer, you obtain positive answer, what to do. And when you obtain correct answers, say positive to positive and negative to negative. So all these 4 conditions, here there won't be any change in weight, so no change. So if you want positive answer, you get negative, so you will add. When you get negative answer and you want positive answer, you will subtract. So all these things will happen with the help of this simple equation. Now there is a concept of something called as Perceptron Convergence theorem. I will give you today a basic idea, so you will see a small derivation next time. So what it means is that when your data is linearly separable, your classes are linearly separable, we can train the perceptron in a finite number of steps. Okay, there won't be a loop which is infinite. So what it means is, suppose I start with this weight, I randomly assume some weight initially, and then I start presenting the patterns one by one with some value of c. Okay, so if I do like this, then the theorem says that you will go to this region of solution in finite steps. You don't require infinite steps. Your computer will not get hanged because it's infinite loop. Okay, so that will not happen. So that ensures that my training will finish in finite number of steps. It may take 1,000 steps, it may take 10,000 steps, it may take say 100 steps, or it may take 10 steps, whatever it may be, but it will not be, or it will never be infinite. So that is what is ensured by Perceptron Convergence theorem. So this is very important theorem as far as programming is concerned. So you can terminate your program in practical case that one can count how many iterations I have done. So maybe 10,000, then I can skip, or you can keep your loop on till you get 0 error. So no error You can keep this condition error equal to 0, or you can terminate your program with number of counts. Since practical data is not linear, this error equal to 0 condition may not arise. Okay, so error equal to 0 condition will arise in case of perceptron only if the data is linearly separable. So this is my line, and this becomes class 1 and this becomes class 2. If this is the case, then I can terminate the things in finite number of steps. So that is ensured by perceptron. So this concept I have given you. So we will start with this concept tomorrow and try to prove that this is the case in case of perceptron if data is linearly separable. So let us stop today.